Our boy Albert Michelson was a professor of physics at the United States Naval Academy. He realized that light's self-interfering properties can be taken advantage of to measure average velocity extremely precisely. If you have seen the double slit experiment, you have seen light's self-interfering properties. The other guy in the experiment, a chemistry professor, Edward Morley, contributed to the design and building of the experiment by supplying a pool of mercury, which the interferometer sat on to isolate it from vibrations and reduce mechanical strain. And because of this selfless contribution, the experiment will forever be known as the Michelson Morley experiment. The interferometer works by using a single light source. The light is split into two paths and rejoined. This is easier to visualize with a laser, but Michelson had to use a sodium light source because lasers would not be around for another 70 years. I'm going to draw out the path the light takes so we can try and make sense of how this thing works. The light leaves the source and hits a 50-50 reflective transmissive mirror at this 45-degree angle. This means that 50% of the light will be reflected up and 50% of the light will be transmitted through. The first arm consists of the light that is reflected up. It hits a mirror that is 100% reflective and now travels back the way it came. After it hits the 50-50 mirror again, half of the light is reflected back to the light source and the other half is transmitted through, traveling down. The second arm consists of the light that is transmitted through the 50-50 mirror. It also hits a 100% reflective mirror and travels back the way it came. It hits the 50-50 mirror again, and this time half of the remaining light travels through the mirror back to the light source and the other half is reflected down. Now, both arms of light, after they have completed their journey, are overlapping, and the two arms hit a screen. If the two arms of light travel the exact same distance, then the light on the screen will constructively interfere, meaning that you have 25% of the total light from one arm and 25% of the total light from the other, so the total amount of light hitting the screen will be 50% of the light from the light source. But if the distances the light travels in one arm is different by a few nanometers, then you will see an interference pattern on the screen that will look something like this. Each fringe is equal to a difference in distance of 1/4 of the wavelength of the light source. Michelson expected the interferometer to work similar to the boat race problem. The river in the problem would be like the ether, and the boat would be like the earth. Here's how Michelson thought about the problem. The earth and the experiment are moving at 30 kilometers per second in some direction. The ether is not moving. Light has to travel through the ether and therefore is moving at the speed of light minus the speed of Earth, because the ether is not moving. This is the same thing as saying Earth is not moving and the ether is moving at negative 30 kilometers per second. But we are using the ether as our frame of reference, so we say that it is stationary. He thought the arm of light traveling perpendicular to the Earth would complete the trip faster, according to the boat race problem. So finally, even if the length of each arm of the interferometer is exactly the same, we would see an interference pattern because the arm of light traveling perpendicular would be traveling faster. And if we rotated the interferometer by 90 degrees, we should see the fringes shift because now the other arm is traveling faster. Michelson expected to see a shift of about 40% of the width of a single fringe. He saw about 5%. And this was about the measuring uncertainty of his experiment. To his complete surprise and dismay, Michelson proved the ether did not exist. This shocked the scientific community at the time. Physicists thought the theory of the ether as concrete. This rocked the foundation of what we thought we knew about light. As it turns out, we would need Albert Einstein's theory of special relativity to determine how light travels. Einstein said, "What if light is different? What if the speed of light cannot change, but time and space change to keep light's speed constant?" And we'll talk about that in the next video. Thanks for watching.